Good evening, everyone. Thank you for joining this talk. And so, as I kind of said tonight, I want to give you an introduction to Earth system modeling. And in particular, I want to look at what is the Earth system? Why do we care about modeling the Earth system? And then I'll spend the second half of the talk looking in more detail as to how we build a climate model and some of the technical challenges associated with that. So firstly, what is the Earth system? And here I want to start by pointing back to Earth, looking at a video of 1 week of images from geostationary satellites. And what I'd like you to do is, while watching this video, think about, maybe take a mental note or of 2 to 3 things that you're noticing from this video. If you're following at home and there's someone else alongside you, feel free to discuss that with whoever is next to you. So, what did you notice? Here, I'm going to mention 3 main things that I noticed, and I'm happy to discuss some more in the questions at the end of the talk if people have noticed things that I don't mention and want to talk about it. So firstly, one thing that I noticed is the daily cycle. That is that night and day cycle that is due to the Earth's rotation. And obviously that's very important for our daily lives, but it's also important for the dynamics in the atmosphere and the ocean that I will be mentioning later in this talk. Another thing that's pretty obvious to me is the clouds. So we have those white and those light blue swirls that are clouds moving in the atmosphere. And lastly, when it's nighttime, we can notice artificial light over the US. And this is obviously a sign of human presence on Earth. And that's something, if you're traditionally signing into astro talks or you're interested in studying other planets, that's obviously something that's quite specific about Earth, is that we have humans on Earth. And humans are obviously, can feel the impact of changes in the Earth's climate, but can also impact the Earth's climate, which we'll be mentioning tonight. Here is a second video, and let's do a similar exercise. This is a compilation of images, again, from geostationary satellites, that covers about 2 years. Again, take a mental note of what you notice. So once again, I'm going to mention 3 things. One thing is that once the clouds that are moving above are removed, what you can clearly see is the continent. You can recognize North America. But by opposition, one thing that maybe you haven't noticed is that actually there's a lot of ocean, and the oceans cover 70% of Earth's surface, which is why we call Earth the blue planet. And the ocean is important because it contributes to redistributing heat around the globe. It contributes to fisheries, if you like eating seafood. And lastly, one thing that you're likely to have noticed from this video is the seasonal cycle. You can see the plants greening in the spring and summer over the US, and in winter you can see the northern US and Canada being covered in ice. So all of these things are part of the Earth system. So when we think about Earth system or Earth system modeling, we really think about this complex system that has interacting physical, chemical, and biological processes. It includes the atmosphere, which we saw with the wisps of clouds moving around, the oceans, covering 70% of the surface, the land, including plant growth, and the cryosphere, that is anything that has to do with ice. That can be glaciers or permafrost or polar ice caps. And when we want to think about a part of the Earth system, let's say here you're interested in thinking about rainfall or precipitation, which you see here. On this schematic diagram, you need to consider the entire water cycle. To be able to represent or to understand rainfall properly, you need to understand contributions from the snow and ice melt, contributions maybe from rivers and runoff, from transpiration from vegetation, and from evaporation from the ocean. It is also a multi-scale problem. In terms of temporal scales, we've mentioned the daily cycle with night and day. We've mentioned the seasonal cycle, and there are all sorts of cycles, and various parts of the Earth system are going to respond more or less quickly to perturbations. So for example, when we think about the weather in the atmosphere, it's a relatively quick response. So we're talking about timescales of days to maybe a couple of weeks. If there's a big perturbation to the upper atmosphere, let's say a supervolcano erupts, it can have an influence that is longer lasting, maybe months to years. In the ocean, we have ocean mesoscale eddies, which are the equivalent to the atmospheric weather. And these ones are longer lasting than in the atmosphere. They last up to several months. In the deep ocean, if you have a change to the deep ocean, it tends to stay for hundreds to thousands of years. And when we think about the cryosphere, in particular, the biggest, largest ice sheet in Antarctica or in Greenland, the ice on them flows, but flows at about maybe meters to kilometers per year. And to have a complete change of the landscape over the ice sheet, we're talking hundreds to thousands of years. So now that I've given you a little bit of an introduction of what I'm talking about when I'm talking about the Earth system, I want to ask the question, why should we care? Why should we want to model the Earth system? And so one important point here is that the Earth system is changing. And once again, maybe if some of you are interested in studying other planets, I think the Earth is specific because we have an atmospheric composition that is changing so rapidly. And so here on this plot, these are atmospheric measurements of carbon dioxide taken at Mauna Loa in Hawaii. And what you see is how since the late 1950s up to now, you have an increase from maybe a little less than 320 parts per million to almost 420 parts per million. And so you have over a 30% increase in the concentration of carbon dioxide in the atmosphere in the last 80 years. And this is important because a change in the atmospheric composition is going to mean a change in heat and the Earth's energy balance. So carbon dioxide is not the only greenhouse gas emitted by humans. We can have methane or ozone. But importantly, the general process is that what you have is that the sun radiation tends to go through the greenhouse gases. It's a shortwave radiation, tends to warm the surface of the Earth, which then emits infrared or long wave radiation. But those greenhouse gases in the atmosphere tend to absorb the infrared radiation and re-radiate it in all directions, including back towards the surface of the Earth. And so by changing the amount of greenhouse gases in the atmosphere, we're letting less heat being released to outer space, and therefore we're increasing the amount of heat that is trapped in the atmosphere and near the Earth's surface. And so once again, in the upper plot here, we have the atmospheric CO2 increasing as a function of time from atmospheric measurements. And here we see the air temperature, the globally averaged surface temperature. And we can see that it's been increasing, and here particularly between, the 1950s and 2012, you have this strong increase of the global air temperature. And that's through that process that I explained of having an increase of CO2 in the atmosphere, leading to trapping of that heat and therefore increase in the air temperature. It's not really the atmosphere that is changing. So here in this plot, we have the energy accumulated within the Earth's climate system. And if you're looking, the atmosphere here is in purple. So it's this little part near the bottom. And again, this is as a function of time from the 70s to 2010. And what we see is that in terms of where that energy that is accumulated on Earth is going, it's really the upper ocean in light blue and the deep ocean in dark blue that are the major players. And so more than 90% of the total and extra energy is currently being taken up by the ocean. And that's important because once again, it points us back to the example of the water cycle of saying we can't understand the climate system if we only consider what is going on in the atmosphere. It's really important to also look into what is happening in the ocean. And also, it's a bit of a warning for us to say whichever warming that we're feeling or measuring in the atmosphere, which we've seen in the previous plot is a measurable difference, is only a few percent of the energy imbalance and the total heat change that is happening on Earth. So we've seen that changing the atmospheric composition means changing the Earth's energy balance. And so we're currently in a transient system where the Earth system is adjusting to the new atmospheric composition. And we're continuing to release carbon dioxide through the use of fossil fuels. And so we're continually changing the system. And so Earth system models are helpful because they point us to what is going on and help us in particular attribute the different changes. So here is a plot to give an example of what you can do with an Earth system model once you have an Earth system model, is saying, here looking at the temperature anomalies, in the upper plot in A, the observed temperature changes are in black as a function of time, again from the 1900s. And the red lines show what climate model simulations show when you include both the human contribution and the natural contribution to changes in atmospheric composition. And in case B here in blue, we have a case where we're running the climate models, the same climate models as here, but simply what we've done is saying we're only looking at the natural changes and not the excess carbon dioxide that humans are releasing in the atmosphere. And you can see that in this case, that blue line is much flatter than the observed temperature anomaly in black. And so this tells us, well, we can't really explain what we're currently measuring if we didn't account for that extra CO2 released by human activity. And so having a model here helps us doing sort of what ifs cases of saying, this is what we measure, but what if humans hadn't been releasing CO2 at all. And that shows us that even helps us explain what is causing what we can measure today. Obviously, another important point that climate models are useful for is to be able to make future projections. And again, testing what if, and testing various futures. So here, this is an example of an agreement. The Intergovernmental Panel on Climate Change agreed across the board to say, these are possible scenarios for the future. So this is the historical emissions of CO2, and then saying what happens if the use of fossil fuels and CO2 emissions continue to rise at about the same rate as historically. That's the red line. But also other scenarios of saying what happens if they continue to increase, here in orange, but at a slower rate, or the two lower emission scenarios in light blue and dark blue, where we're saying, oh, we decide that those emissions will flatten or will decrease in the future. And so once we've agreed on those scenarios for the possible futures, we can run climate models into the future and say, what is the response of the Earth system under that condition? And so here, this plot is showing the global average surface temperature change. Again, in black here is the historical temperature change that is measured from observations. And then here is what climate models project to happen in the future. And in the red case, which is high use of fossil fuels, emissions continuing the way they've been going, we can see that there's up to a 4-degree difference in the future in 2100. Whereas if we have a lower emission scenario with a limited use of fossil fuel in blue, the increase in surface temperature, it's still an increase, but it's only an increase maybe of 1 degree. And with full coupled climate models, we can look not only again at air temperature, but also at other consequences such as the global mean sea level rise. And so here's our past sea level rise up to, I think, 2010, 2012. And here is again the projected future global sea level rise, with red the high emission scenario and blue the lower emission scenario. And so people can use that to make strategies about saying, you know, is it in our interest to limit fossil fuels or not? And evidently here, we see that changing, even just by limiting the rate of emission of fossil fuels, can make quite a big difference in air temperature, moving from a 4-degree increase by 2100 down to a 1-degree increase. And here, maybe 0.7 meters to 0.4 meters by 2100. And just a note is that these results are done with the full range of climate models that exist around the world. And so the shading here in red or the shading here in blue are showing the range of results that different simulations or different climate models around the world have projected. So hopefully, I've convinced you that it's in our interest to work in modeling the climate and doing a good job at it. And so I want to take in the next part, I really want to look into giving you an introduction of how we build a climate model. And I'll start with a pretty simplified  recipe. So as we've seen when talking about the natural system, the Earth system, we've seen that it's this complex system with various parts: ocean, atmosphere, land, ice, and that different parts react to changes with different timescales. And so traditionally, climate models include different components, such as an atmosphere component, an ocean component, a land ice, which are all the ice sheets and mountain glaciers, and sea ice models. And those are built by people who are experts in that particular field. And then we put them all together to talk to one another through a flux coupler. And so that flux coupler is gonna basically transfer information from the atmospheric component to the ocean and back, so on and so forth. And so in the rest of this talk, I'll mostly be talking using examples from the ocean, because that's my background and that's part of what I do as a researcher. But I'm more than happy to discuss either in the questions or later offline about whether there are examples for other parts of the climate system, or to put you in contact with people who have more expertise in those other parts of the climate system. Okay, onwards to our simplified recipe of how to make a climate model. Step 1, chop the world in blocks. So what we traditionally do is that we define a grid that we're going to run our climate models on. So here, for example, in this schematic, you can see that the atmosphere in gray is broken down in blocks, and the ocean in blue is broken down in blocks, and so is the land. And then in each cell, in each block, we're going to try to resolve the physical processes that take place at that location. And then each block communicates with the neighboring blocks to transfer information of what is going on. If, for example, you have a storm coming through the atmosphere or a hurricane coming through the Atlantic, it will propagate from cell to cell. Then in each cell, we want to keep track of the important variables, and we want to input known ocean physics. So for the ocean, in each cell, we want to track temperature, salinity, density, which is related to temperature and salinity, pressure, the velocity of the water in that cell, and then all sorts of chemistry, such as the concentration of carbon, nitrogen, phosphorus. Other types of tracers, we can think about phytoplankton, which is the biology, if you want, the plants of the ocean, or the zooplankton, which are the small animals that grow in the ocean. And then for each cell, we want to apply known laws of physics. And so basically we want to ensure that we have a conservation of mass, momentum, tracers such as the temperature or salinity that I talked about. And so I'm not going to go into detail of all the equations. I'm more than happy to do so if people want to do so offline. But here I just want to give one example of looking at conservation, for example, of momentum. And just showing you that those climate models are really based on the laws of physics. We go back to the idea of what forces are applied on a parcel of fluid. And we're applying Newton's second law of saying mass times acceleration equals the sum of forces. And so The forces that are at play in the ocean to move water around are all of these. So the pressure gradient force, the gravitational force, the Coriolis force, which I'll explain a little bit more, the frictional force, and boundary forces. And so I'll just quickly take you through those different terms to give you a sense of what are the main forces that are at play in the ocean. Well, the gravitational force, I hope that's pretty self-explanatory. From the Earth gravitational field, keeping water and keeping us seated on our seat. Here, this is the frictional force, which is a function of the velocity u. It tends to slow down a parcel that is traveling very fast due to friction and viscosity. And so in the case, for example, of honey or maple syrup, very viscous, it tends to be harder to have a high-speed flow. And in the case of air, you have a much smaller viscosity. And so here we have our parcel. If it's traveling to the right with velocity, that force tends to oppose the current traveling speed. One example of boundary forces might be the wind at the surface of the ocean. And so, for example, if you have wind blowing over the parcel of water, if that it can accelerate the water, it can push on the surface of the water and accelerate the water in that direction, in the direction that the wind is blowing. The pressure gradient force. So this is a force that pushes fluid parcels from high to low pressure. So if you have a center of high pressure in the atmosphere, for example, an anticyclone, or the fluid tends to flow, so either in the ocean, in the atmosphere, tends to flow from a center of high pressure towards a low pressure system. And here's the Coriolis force. That is an apparent force that is due to the Earth's rotation, and it acts to the right of the velocity in the northern hemisphere. So if you have air or water, a fluid parcel that is traveling in this direction to the right, the rotation of the Earth is going to tend to pull it to make it veer toward the right in the northern hemisphere. And so the largest forces in the atmosphere and ocean are the Coriolis forces that tend to balance that pressure gradient force that I talked about before. And so if we start again with our high pressure to low pressure, our fluid parcel here tends to, through the pressure gradient force, wants to flow towards a low pressure system. But because of the Earth's rotation, it tends to veer to the right. And so as a result, instead of flowing directly towards the low pressure, it tends to flow around, for example, around the high pressure system or around the low pressure system. And so that is what is responsible for the sort of weather patterns that you can see, such as anticyclones, if you're looking at weather forecasts, or hurricanes. So hurricanes have low pressure. And so instead of traveling straight towards the center, you have this swirling pattern where Coriolis force is deflecting it so that it swirls in a spiral. And so this is just images from Hurricane Marie from today, actually. And for those of you who are interested in other planets, that is also why we can see vortices on other planets such as Jupiter. It's again the balance of Coriolis and the pressure gradient forces. Okay, so once we have all our equations for different variables, including making sure we have conservation and momentum, conservation of mass, conservation of temperature and salinity, Then it's all about transforming the physical equations into computer language, make it a computer model. And so here I'm just giving a snapshot of the source code of like the ocean time stepping. So how we're moving in time in our ocean model. That is the source code from the DOE ocean model, MPAS Ocean, which is freely available on GitHub if you're interested to look at it. And so the short story here is just to say that step takes a lot of programming, takes a lot of people being involved. If it's something that you're interested in, I'm more than happy to talk to you about this. I'm more than happy to direct you to people who do that. Yeah, I'm not sure it's appropriate for a general audience. And there's also a user guide that can explain and relate the physical meaning and how it's implemented in the ocean model. And step 4 is to run this on hopefully supercomputers. So only like a low resolution global ocean model can be order of 1 million grid cells, and usually might be run with time steps of order from minutes. And so if we want to have a simulation that lasts several years, it really takes a lot of computing resources. We're talking millions of core hours. And so that's one great advantage of being at LANL, is having access to computational resources. And so here's giving you an idea of the result. So this is a video of the ocean surface speed from MPAS Ocean. And you can see, so in color is the ocean surface speed, and you can see various features, including the Gulf Stream here, flowing along Florida and the eastern seaboard, and then traveling across towards Europe. And so this strong current brings a lot of heat towards Europe. You can also see a lot of equatorial dynamics, where you have equatorial instabilities here, those big swirls. And so this is just giving you an idea of the level of detail that we can work towards on a global ocean model. And again, that is only the ocean component of a climate model. The DOE climate model has also an atmosphere and a land and a sea ice model. So for the last part, I do want to bring up some of the challenges with Earth system modeling. So I gave you this simplified step-by-step recipe in how to build your own climate model. Good luck with that. But I guess I really want to highlight that every time you're thinking about modeling, and if some of you are scientists and working in modeling in other fields, I'm sure this will sound familiar. A lot of the question is, okay, what is the purpose of the model that you're building? And therefore, that should inform what to represent and what you think at what cost. We can't represent everything in those models, even with large computational resources. And so it's always a cost-benefit analysis of saying, are we capturing the important things that we need to answer research questions? And so I want to give a quick example about Antarctic ice shelf melt, a little case study. I'm picking this case study because it's partly my field of research, and it's something that the team at LANL is actively working on. And it's a pretty important aspect. Earlier today, I just Googled news headlines, and you can see headlines such as, Antarctica could melt irreversibly due to climate change, or melting Antarctic ice will raise sea level by 2.5 meters. Or melting Antarctic ice will raise sea level and might cause humanity to give up New York. And so it's definitely something that has a lot of implications for societies in terms of coastal protection, in terms of the major cities being near the ocean, and what we plan for in the future. So a quick introduction to Antarctic ice shelves and Antarctic ice shelf melts. So this is a picture taken in front of Antarctica with a research ship to give you a scale. And Antarctica is a continent that is covered by ice. That's what we call the ice sheet. And then part of that ice flows down towards the sea. And we have this section, which we call an ice shelf, which is a part of ice that is floating on the ocean. So if we look at a schematic, we have here the ice sheet that is grounded on land. And it ends with this little, it can be quite big, but here on this diagram, it's little ice shelf, which is a floating part of ice. And the important part is that the friction of this ice shelf being here tends to slow the flow of the ice sheet into the ocean. And so this is in active contact with the ocean. And so if you have a warm ocean current, and for example, we often think about the circumpolar deep water, which is a relatively warm water in the ocean. If it comes in contact with this relatively warm water, this warm water can start to melt, to eat away at the ice shelf from underneath. And therefore, if we're eating away at this part, we tend to accelerate the flow of the ice sheet into the ocean. And by adding what is currently stored on land into the ocean, we're raising sea level. And so for this case study, a lot of questions that we're trying to tackle in research is saying, how are ocean changes melting the Antarctic ice shelves? What range of sea level rise do we need to be prepared for? And there is again this big challenge of saying, okay, if we want to think about this question, what do we need to represent and at what cost? And so here, I'm just giving you an idea of the range of spatial scales that we might want to consider when we're trying to answer this problem. And so these are large spatial scales. Again, the global, the global increase in atmospheric CO2. So that's thousands of kilometers. The full scale of the Antarctic continent, that's thousands of kilometers. And then at slightly smaller scales, we consider, okay, here is the location of a big ice shelf. And this little plot here shows the topography, the sea, the floor, the sea floor underneath that ice shelf. And so in particular, we're worried about this ice shelf because it's very large, but it has a deep channel on the east here that can allow warm water to flood in. And so here we're starting to talk maybe hundreds of kilometers. Or the ocean dynamics, the little swirls in the ocean that I talked about as the weather of the ocean, are a very important player in bringing heat in this channel, for example. And these are more the scale of 1 kilometer. And then when we get very close to the ice, if this is the surface of the ice, the melting of the ice is actually happening at a scale of maybe 10 centimeters or 1 centimeters, very, very close to the interface between an ice wall and the ocean. And so, unfortunately, it's not realistic for us to say we want our model to consider every millimeter to have a grid that is 1 millimeter by 1 millimeter, because that would be way too costly to both be able to resolve the large scales, the entire planet, and every single millimeter. And so we have to make choices as to what we decide to represent and what we decide to simplify. And so, for example, in the current level of research that is happening at LANL, we're running a global model with the entire scale of Antarctica, including as fine scale as some eddies, maybe 5 kilometers. But we decide this we cannot represent, it's too small scale. And so we use simplified representations called parameterizations, where we say, let's agree that the melt, from other studies, we can say the melt is actually proportional to the temperature squared. And so we're using these laws to simplify this process, because this process is happening at too small a scale for us to represent. So here is an example of a simulation from Pajarito Ocean. And here you see the salinity in the ocean flowing underneath the ice shelf. So if we were to look from an image from the top, from like a satellite, we would see all this here, this section is covered in ice. And what we're interested in here, obviously, is to say, oh, maybe we have meltwater coming from underneath the ice shelf that is changing the ocean properties here by becoming fresher in blue than the surrounding waters. And so there are different strategies to try to sort this problem. There's what I said about using parameterizations, simplified representations of some physics that we cannot actively represent because maybe they're too small scales. One important aspect for that DOE climate model is that we have the potential to do variable resolutions. So instead of saying every block that we chop the atmosphere or the ocean in has to be the same size or has to be a certain set degrees of latitude and longitude, that enables us to pick where we think it's very important to represent smaller scales. And so this here is an example of a variable resolution mesh where most of the globe is represented where each block is about 30 to 60 kilometers. And then in the Southern Ocean and near Antarctica, this here is the tip of the Antarctic Peninsula, we're using a much finer mesh that is down to 6 kilometers. And so again, the idea is to say, can we extend the range of spatial scales that we can represent? And because it's too costly to represent small scales everywhere, in this configuration, we decide to represent the finer scales near Antarctica. Because what we're trying to look at in terms of research question is how the ocean is interacting with the ice in Antarctica. And so that allows us to resolve the effect of mesoscale eddies, which are about kilometer scales in the Southern Ocean, and to keep the cost of the ocean model 3.5 times less than if we tried to put this high resolution everywhere. Okay, so to conclude, in summary, I gave you an introduction to the Earth system, showing that this is a complex system that has interacting ocean, land, atmosphere, and ice. And by definition, it's a very multidisciplinary field. And it's also multi-scale, both in terms of temporal scales from the daily cycle down to century or millennia. or temporal scales, where we might want to think about the melt between ice and ocean happening at the millimeter scale, but we want to consider global scales that are that are thousands of kilometers. Earth system models are really important because that allow us to go beyond what we can measure and beyond the present. That enables us to establish links, what we call attributions of running, saying, if humans had contributed fossil fuels, what would the climate look like? And they also allow us to make projections into the future of saying, if we pick a particular scenario for the future of CO2 emissions, this is the sort of consequence that we can anticipate to have in terms of atmospheric circulation or ocean circulation, droughts, heat waves, and therefore to make strategic decisions about that. Earth system models are those large computer codes that are built on the laws of physics. They're often run on supercomputers because of the huge computational costs of trying to represent this multi-component, multi-scale system. And we have made a lot of progress with climate models. If you go a decade or two in the past, the results from climate models look quite different in terms of the fine scale dynamics that they are able to represent. But in general, one of the big challenges of modeling, it's definitely the case in Earth system modeling, but it's also the case in other types of modeling if you're involved in other fields, is that we definitely have limited resources. We always have to make strategic decisions about what we represent versus what we simplify. And these decisions depend on the questions that we're trying to address and the resources that we have. And there are various tools that we can use, such as relying on the work of other people who maybe study smaller scales or maybe study larger scales. But we have to set a limit to what we can effectively run in our system models. So if you're interested in learning more, obviously feel free to ask questions right now as we're going to move to question time. You're also welcome to email me. And there are plenty of other resources out there if you're interested, for example, to learn more about the state of climate or the potential consequences on various parts of the climate system. There are various reports that are freely available online that details the state of the science in terms of climate, and both in terms of observed present day changes, but also in terms of future changes. And I really like this particular website that explains the conclusions from this report, the AR5 report, and in particular tries to address some of the climate myths or misconceptions that people might have about the results. And if you're interested in learning more about the DOE climate model called E3SM, please go to the website. Please, if you're interested in the code, it's available on GitHub, and there are various data sets or videos that are available on Zenodo. So now it's time for questions.
Thank you, Alice. That was really interesting. And we do have some questions in chat. A reminder to everybody, if you have your questions, that's where to put them. Bring up the chat window and type them in. So our first question is, how do you measure sea level rise to get a mean?
What was the last part of the question? I'm not sure I got the...
This was when you were talking about mean sea levels, and the question was, how do you measure the sea level rise and get a mean sea level rise?
Okay, so sea level rise, we get it from different locations. Historically, we have tidal gauges in different parts of the planet, and so those are helpful because they have a very long time series. And what's important, obviously, is that you want to average that in time so that you don't get just the tidal cycle, let's say. Nowadays, we can also measure sea surface height from satellite with altimetry. So that's another big component that has changed since we have satellites. And then I guess a mean sea level rise, it looks into mostly, well, temporal and spatial averages with all the data points that we have.
All right, next question is, what are some other examples of boundary forces on the ocean besides wind?
Okay, well, friction in general is one that we think about a lot. So you can have, again, wind at the surface, but you also have what is happening at the seafloor, at the bottom of the ocean, where you have a moving ocean current going over things that are very similar to what we see on land. You have mountains, you have valleys, and so that can contribute as well through friction. And obviously at the coast, we also have sort of lateral friction from having a continent that the ocean is flowing against. So that's another major boundary force.
Okay, and someone asked, you mentioned that 90% of the increase in heat is being taken up by the ocean. How might this change in the future with increasing CO2 atmospheric abundance? Will the ocean's ability to take up heat saturate?
That is a very good question. That is a question that a lot of climate scientists are thinking about and working on. So again, we have 90% of the measured energy imbalance going into the ocean. And we expect that to continue in the sense that because of its large heat capacity, the ocean is able to store a lot more energy than the atmosphere. And so in general, we do anticipate that the ocean will continue to be a big heat reservoir. But there's a lot of question of saying, okay, that's kind of the total averaged picture. But if you think about what are the processes that allows the ocean to store heat and store carbon dioxide, for example, a lot of people are looking into if you have something like that, is it likely to come back to hit the atmosphere just maybe 100 years later or something like that. So that's a problem that people are thinking about, particularly in terms of, let's say, the ocean being a reservoir of carbon dioxide.
Okay, let's see. As computers become more powerful and resolution is improved, do you anticipate qualitatively different global climate results, or are you seeing convergence in the results?
That's a very good question. So maybe, do I have my slide? So the IPCC, which is the Intergovernmental Panel on Climate Change, is a worldwide organization that gathers the information about climate science and the state of what we understand about the climate. And that has been going on for many years now. And basically the major differences is just that we have higher confidence into the results that we predicted decades ago. So there is definitely, in terms of global behavior, there's definitely convergence in that we're not seeing any contradictory results from today's models compared to models a decade earlier. In terms of, for example, our ability to make projections for smaller scales or specific parts of the Earth system, we are getting better at doing that. It's, for example, temperature, we have a relatively consistent picture. Precipitation, rainfall, generally requires a lot higher resolution. And so we're making more progress on the things that require us to resolve the smaller scales, because we're able to model at higher resolutions. But overall, do the general conclusions about greenhouse gas emissions and air temperature increases change? No, they're very, very consistent, and they're very consistent across different tools that we look at.
Okay, and I have two related questions here. One person asks, no, actually it's the same person. What fraction of the Earth's water is fresh water? Do you model lakes and rivers? And also, what fraction of the Earth's water is water vapor?
That is a good question. I wish I had an extra slide. I'm going to try to answer off the top of my head. It's actually a very small fraction. It's definitely less than like 10% in terms, maybe even less, like more order of 2% for what is accessible freshwater. In that a lot of our freshwater resources are stored in ice. So stored in mountain glaciers or ice sheets. That's our main reservoir of fresh water. And yeah, I'm gonna have to punt on the percentage of water vapor, of water altogether that is contained in the atmosphere. If I can have access to those comments afterwards, I'm more than happy to send you the details about that. To answer the question as to whether we model them, yes, we do model freshwater bodies. Again, if you have coarse resolution, low resolution, it's hard to model. We're not going to model every single lake, especially if it's smaller than what we can resolve, in a grid cell. But that's often part of the land model. That includes vegetation, includes lakes and rivers and things like that. But there is definitely some representation of lakes, particularly the big ones, and major rivers.
Another question, don't you need the moon to measure tides?
To measure tides, I'm not sure I understand the question. We in real life, we can measure tides by measuring the shift in sea level. In models, we could go the way of trying to include a moon that we need to represent tides. What we normally do is that we apply, if you look at tidal charts can give you the various components that constitute tidal modes. And so what we do in models is that we add the effect of the moon without simulating the moon itself. So we're just adding those extra modes due to the moon and the various tidal cycles, astronomical forcings, without actually including the moon or the sun as gravitational bodies. I hope that answers the question, but feel free to follow up if it doesn't.
How will the El Niño oscillation change with an overall warming of the ocean?
That is a very good question. So people anticipate that it will be affected by the sort of global changes. In particular, that we might expect, there is sort of one mode, a positive phase, which is El Nino, and a negative phase, which is La Nina. And so people are concerned that, for example, we might see higher frequencies of El Nino compared to La Nina, or higher intensity of the modes. And so that's something, for example, that you can find, I don't know if it's in the State of Climate Report 2019, but it's definitely in the IPCC AR5 report. And here the summary for policymaker is a very short, maybe a dozen pages or something like that, that gives kind of the major conclusions. So if you're interested in a particular question, you can look at the summary for policymakers And if you don't find the information, you will probably know which section to look at. And so that's a very accessible type of report because it's not geared toward scientists only.
And we have two related questions. One is, what are some of the climate misconceptions that you encounter most frequently? And a related one is, many people say the current warming is only part of natural variation that has occurred for eons. How do you know the current warming is not just a statistical fluctuation?
Wow, those are very good questions. I might need your help, Akana, to make sure that I answer all of those because there's a lot to say on that.
I can split them up if you want. They may not be as related as I thought.
Just remind me maybe when I've talked for a little while. So some of the climate misconceptions, one big thing is definitely the climate versus weather misunderstanding. And so the weather is really something that we experience locally, and that can change from day to day. And if we have, let's say, a warm winter, some people suddenly start believing in global warming. And then we have a cold winter and people start believing in global warming. And that's a misunderstanding of what scales we're talking about when we talk about climate. And so I think it might be on the NOAA website, but one of the illustrations that people use is saying weather is to say, you know, do you need an umbrella as you're getting out the door today? And climate is more looking at your closet and what type of gear do you have in your closet? Like, do you have winter gear? Even if you don't need to wear it today, is it important for you to have it for the climate of where you live? And so what we're talking about when we're talking about climate change is saying, are winters going to become warmer statistically? And it doesn't mean that we can't have one cold snap in one location, for example. You're still going to have cold snaps in various locations. But on average, if you look at the entire globe, you can see that if there's a cold snap, let's say in northeastern US, the rest of the world might still be warmer than normal, than average. And so that's a little bit difficult, I think, for people to get, because I think, you know, as humans, we tend to remember, you know, the weather that we had this week. It's really hard for us to intuitively have a sense of what climate looks like, which is why it's really important to have those observations, because long-term observations can show that even if, you know, the temperature decreased, let's say between this year and last year, we're still the third warmest year on record. So yeah, it's really important to have observations and to have observations in many different locations, because again, one location can be cold, but on average, the other locations might still be warmer. Okay, that's one climate misconception. The other climate misconception might be the second question that were received, saying, oh, it's only natural variability. And so here again, some of what models bring us is the idea of saying, okay, if it was only natural variability, if we didn't have the emissions that humans have generated, would we be able to reproduce what we're observing? And so the plot I showed earlier with the observed air temperature increase, we can see that it's nearly impossible for climate models to reproduce that if they don't have the human influence, the human carbon dioxide emissions. So that's one of the tools that we're using. Another tool that we're using is looking back to the past. It's a little bit harder because we have less direct observations. They're generally proxies. And we can see that in the past, there have been changes in temperature, in climate, but none of them have such a rapid change as what we're seeing. Even what people, looking in paleoclimates talk about, abrupt changes take place over hundreds of years, thousands of years before they reach a peak. And here, the rate that we're seeing since the beginning of the Industrial Revolution is really unprecedented. And so, yeah, another thing that people throw is that, the climate has changed in the past, and therefore, the climate can adapt, or the ecosystems can adapt. And yes, theoretically that's true, but the faster the change that we have, the harder it is for things to adjust to it. And normally, if the change happens over thousands of years, it's much easier for ecosystems to adjust. If it happens in the case of, 50 to 100 years, it's really hard for example, ecosystems to readjust, species to migrate, or to change accordingly. So it's very much an unprecedented rate of change in terms of what we're seeing.
Okay, since CO2 is such a tiny fraction of the atmospheric composition, how can it make such a huge change in global temperature? Wouldn't water vapor or other greenhouse gases be more important?
That's a very good point. We talk a lot about carbon dioxide. I think it's mostly the relative strength of carbon dioxide as a greenhouse gas and the concentration that it has in the atmosphere. Methane, for example, is much more potent in terms of greenhouse gases, but so we need to consider it. It's a big part of the contribution, but it has slightly lower concentration. So if we have the concentrations of methane or the change in concentration in methane that we see in carbon dioxide, we maybe would be talking mostly about methane, but I think both of them are really important ones. For water vapor, it's an interesting point. Yes, water vapor can have a greenhouse gas effect, but the main idea again is that there hasn't been a lot of change as to the amount of water available. And there is a feedback in that as the planet warms, let's say from CO2, we're allowing more water to be stored in the atmosphere because the atmosphere is warmer. So there is a feedback through water vapor, but the main difference is that the carbon dioxide is traditional, let's say from fossil fuels, is traditionally stored. It's stored in oil, it's stored in gas underground, and therefore it's not normally, sort of naturally, flowing into the atmosphere. And so what human activity has done is that's just a consequence of industrial revolution being based on fossil fuels, is that we've just added a new component and a new sort of channel from something that was stored underground to the atmosphere. That's why I think we're focusing on it in terms of policy and in terms of human impact. Again, it's the change that is really important.
Okay, and here's a question I think we all care about. Some 50-year forecasts predict arid and desert-like weather for New Mexico. How reliable would you expect this type of forecast to be?
That's a big question too. So again, in general, I think our confidence in climate projections are that we're very confident for sort of global terms. We tend to be less confident for local terms. So again, about the difference between weather and climate, if someone asks me, is it going to rain in Los Alamos on October 2nd, 2053 or 2100? I don't think I can answer that specifically as a yes or no question. In terms of probabilities, I do think that we have a very high confidence that air temperatures are going to keep increasing globally. And yeah, and so that's a very likely, again, it's slightly dependent on emission scenarios, but for the next 50 years, I think we're locked in for increased air temperature. And there are various studies that focus a little bit more specifically on the US, southwestern US. And so I would love to point you kind of more specifically to those. I don't want to misrepresent their science, but I do think that the type of pressure that will be on water resources in this US Southwest are likely to continue to increase. So I do think in terms of sort of thinking about long-term water management and water resources, I think it's very important to take that seriously.
And here's one related to what you were talking about water vapor in the previous question. Although water vapor is an important IR absorber, it cycles out of the atmosphere very quickly. But could water vapor get into the stratosphere, which is normally extremely dry? Might that make a bigger difference?
So I do think that if greenhouse gases, including water vapor, end up with a longer residence time in the upper atmosphere, that is likely to make a bigger difference. Whether that's likely, I'm honestly not sure. I do think it would take a lot to change the humidity in that high a part of the atmosphere. But again, that would be my level of answer as an oceanographer.
How much of the California fires are related to global warming versus forest management?
So they have been studies looking at the occurrence of wildfires. And so again, in the question about, are we talking about weather or climate? I do want to be careful that we can't necessarily pick out one particular event and say, this one was triggered by global warming. What global warming is doing is that it's amplifying things that are already like that, a spark starts. It's amplifying that by creating conditions that are favorable for more frequent wildfires, more intense wildfires, and maybe some that spread faster. So people have definitely pointed to say the intensity of that wildfire is likely to have a contribution from the climate and the fact that global warming is part of the picture. Again, it's just a little bit careful in terms of communication that ultimately it takes a spark to start a fire. But what global warming is doing is just increasing the probability of having fires. So not necessarily one specific fire, but a very bad fire season. And maybe, again, fires that are on average bigger and more intense.
Okay, well, those are all the questions that came in from viewers. Alice, thank you so much for sharing with us tonight. And everyone, please visit the PEEC website, peeknature.org/events for additional talks like this one. Thanks again for tuning in, and good night, everyone.
Thank you so much.